Okay, today we will be starting this lecture 2, data representation. So last week we worked on the unit 1, creative development, okay, creative development, and that is a single unit. So now we move on to the second unit, that is actually data and the information, okay, data and the information. And data and information is very important right now, okay. So if you look at the data science, okay, data science. If you look at the data science and look at, okay, this one, okay, this one. So let me show you this one. So you look at what data science is. You need to learn the computer IT, okay, computer science, IT, math, and the background knowledge, right? And these three domains together is actually data science. Okay, so data science, you need to combine the knowledge of computer science, math and stats, and also domain knowledge. So this domain knowledge very likely would be business or biology or maybe electrical engineering anyway. Okay, this is data science. So data science right now is very important. And in our AP computer science, 7 big ideas. Last week we talked about it. It is actually creativity, right? Creativity. And then a second one is abstract, right? Abstraction. Okay, and then third one, kata. Okay, third one is data and information. So data and information is one of the 7 big ideas. Okay, and then another one is algorithm. Okay, and then programming, and then internet, and then global impact. Okay, remember to use CADAPIG to remember your 7 big ideas. Okay, so data is very important. I would say that the principle of computer science would be important. One is data and the information. Okay, another important component would be computer hardware. Okay, computer hardware and networking. Okay, and internet. That actually another domain. Third one would be programming and the algorithm. So basically, I mean, if you look at today's computer science or data science, very important, it would be 3 major components. One is data information. The other one is programming and algorithm. Another one is for computer hardware and the networking. These are 3 major branches. Okay, 3 major branches in the today's computer science basic principles. So it's a very important topic right here. Okay, so this unit actually is very important. So let's get started for the data representation. So we have data representation, and then this was part 1. We also have data compression as a part 2 for lecture 2, and then lecture 3 we will be on information. So lecture 2 is on data, lecture 3 is on information. Okay. Okay, let's get started. So data and information is one of the important idea. Okay, so this unit is all about how computer represent data and how they can store and process ever increasing quantity of it. Okay, so here it is about 17 to 22%. Okay, 17 to 22% of the AP exam. There are 74 problems. So if we have 20%, that's roughly about 15 questions. Okay, 15 questions. So first one is binary numbers. Okay, binary numbers. So before we move on into the binary numbers, we need to know about abstraction. Okay, abstraction. So basically, data. Okay, so what is data? Okay, data and the datum, right? Data, datum. So these 2 terms. Let's see, Alex. Okay, Alex Zhang. What is data? What really is data? In your word, what really is data?
I guess facts and statistics and stuff like that?
Data, no, data is not that much. Okay, data just a piece of data. Say, let's look at it. A very simple way to look at it. 1 is data, 2 is data, right? The 3 address is a data. It's a piece of data, right? 32 pound is actually a data, right? A piece of data is very important, very simple. So data is actually singular, okay? Data is a multiple. So data is very simple. Data just some number you see on the street, okay? Speed limit actually 65 miles per hour, okay? So those are data. Those are data, okay? So those are data. So basic data is very simple. Okay, data is just something that you can see from anywhere. Okay, from anywhere. So here, let's see. We have physical world. Okay, physical world. Okay, we have physical world. So physical world, we may have this 1, 2, 3, 4, 5. Okay, 5 stone. Okay, 5 stone. So this 5 stone, we actually represent it as a 5. That's one way you can represent it. You write it down as binary, it's like this. You write it down in Chinese, it's like this, right? So this process actually is abstraction. Okay, from the real physical existence to a certain symbol, right? Or even some people use tally, right? That's called abstraction. And the data actually is what you actually abstract from the physical thing, okay, that become your data. So right here, okay, right here, we have a pizza, right? A pizza, so this one is 1 pizza, right? But 1 pizza, and then here we actually can slice it. Okay, so each one of it actually is 1 piece. Okay, and this 1 piece of pizza actually what? At least one pizza, one whole pizza actually would be equal to a piece of the pizza, right? So in the middle, actually, we already process it. We already process it in our mind. Basically, what we already perform some abstraction. We already perform some abstraction. Okay, you can represent the whole pizza as 1. That's 1 piece of whole pizza, or you can represent it as a piece of data, right? But no matter 1 or a, there's a unit. The unit is 1 whole pizza or a pieces, right? There's a unit, but 1 or a actually both are data. Is that okay? 1 or a are both data. So basically, data by itself is some sort of representation of the physical world. Okay, it's not even go up to the statistics or math. It's just some sort of abstraction. So talking about this, let me jump directly to the lecture 3 part. Okay, before we go into the binary number and more abstraction. So let me open the file for the next lecture, the information. Okay, the information. So right here, let's look at this one. Okay, let's look at this one. So we talk about data science. Your real world, okay, your real world is actually maybe 5 pieces of stone, and your raw data you have is actually what? 5. That's the raw data you collect. Okay, raw data compared with something that you process. So here this is the raw, okay, raw beef. And this side you already make decisions. So this one is cooked data. Okay, so here you have the cooked data. Something raw and something cooked. Okay, so you something processed, it already being cooked. Okay, so raw data is 5 pieces of the stone. So let's look at this. Okay, so that's the first step. You actually need to collect the data, and then you process it, and then you clean it, and then you send into some sort of exploratory data analysis, and then machine learning algorithm, and then producing the data product. Okay, so this whole thing is the flow of the data science. Okay, this whole thing is the flow of the data science. But now let's actually look at, first thing is like you have, let's assume that, okay, let's assume that this is one example. There's a process of abstraction. So let's actually look at a different way. Okay, so you go to take a SAT test. So they give you a answer sheet, right? So answer sheet, actually you bubble it. Okay, bubble it. So A, B, C, D, E. Okay, so you bubble it. Okay, so you bubble it, and this bubble things, you use a scanner or card reader. Okay, so you use a scanner. Okay, you use a scanner to scan. Or card reader, scan in, and then you create A, B, C, D, E. Okay, that's the data. That actually is your answer sheet. So the data being scanned in like this. So from here to here, this is physical. Here is data. So this data we call it raw data, unprocessed raw data. We just know about this one actually is raw data. Okay, it's actually unprocessed. Okay, so some part may read it wrong. So actually may have X, may have missing, okay, whatever. So they may have something wrong. So that's raw data. Raw data you may need to clean up. Okay, may rescan again, may correct and may do something. Okay, so that raw data. So after raw data, you want to process it. So you process it, and then you actually would have a standard answer. So every time you submit your answer for AP ComSci principle practice exam, so I may have a standard answer to check with it. So these two we check together, and then we say, okay, your English reading portion is 800, okay, or maybe 750, okay. So based on this comparison of the standard answer and your data that you scan in from your reading card, okay, the result that we obtain from the scanner is raw data. But when we process it a little bit, we get the first piece of information. This information is your SAT English score that already being processed by certain scale based on the human distribution of the IQ or whatever. You get a SAT score of 760 or 650. Okay, that is a piece of information. Is that okay? That's a piece of information. So that becomes a piece of information. So basically right here, we are talking about the physical world. Okay, physical world, you actually has what your bubble is physical world. Okay, and then go into data, raw data. So raw data actually you get A, B, C, D, E. Okay, and then you process it, become information, right? Information is 800. Okay, 800. Okay, and 800, that's the information. Now the next level is actually knowledge. Okay, the next level of the information is called knowledge. So this 800 is your SAT now. Now actually, let's look at the San Jose State. San Jose State. Okay, so SJSU. San Jose State decided to find the student that admitted. So they use an equation called eligibility index. Okay, it equals 800 times GPA plus what? Plus SAT score. Okay, and this one is a rule. That's an equation, right? That's an equation. Based on this score, they will choose student. So that's the rule, the knowledge rule that actually we make decision based on this rule. So that information will become a rule. The rule by itself actually is a knowledge. Is okay, knowledge base. knowledge base. So that actually is a knowledge. So that one we will see that, okay, that one we will see that, okay, San Jose State student, so SJSU, okay, San Jose State, okay, GPA and the SAT. So there is a certain distribution for San Jose State is looking like this, okay? So based on the SAT and GPA score, you do have your SAT over here. That's your x-axis, okay? Your x-axis. So let me show you in the tab, okay, in the new tab. So basically, you have this x-axis, you have the SAT, y-axis, you have your GPA, and the eligibility index will be an equation of what? 800 times GPA plus actually SAT. That's actually an equation. So that equation may be something like this, okay? So maybe this side actually reject, okay? Maybe this side accept, okay? So there is a rule, and this rule become a knowledge. So from your physical world, you obtain data, and then you process it, become information that SAT 800 or 760, then put into certain equation that called knowledge, okay, knowledge. So knowledge actually is a rule based, and you can make business decision based on the rule, okay, that's actually knowledge. And the next level of the information, so this one actually, you see the eligibility index, San Jose State impaction, okay, result. Okay, this one, I'm not making it up, okay? Actually, the eligibility index is used for San Jose State, okay? So here, let's see, actually, they have the impaction result, okay? So they have the impaction result. So this here, we have impaction result. So there's a 2022. Let's look at some older year, okay? So for 2019, okay? So here, say, each major has admission to the minimum, the program's minimum eligibility index. So your business administration may have, say, 3,750, okay, for the accounting and finance, okay. Computer science may have 4,675, okay. So each major have different eligibility index. And this eligibility index actually is just based on the so-called 800 times GPA plus SAT. So this one is a rule. I'm not making it up. It's actually the real rule being used by San Jose State. It's this equation, okay? And that is a knowledge. So what I talk about here is like, okay, you hear the word that actually have the data, also have information, also have the rule. Next level will be intelligence. Okay, next level will be intelligence. So what is intelligence? Intelligence means that, okay, intelligence is beyond just a formula. Okay, so by SAT score and GPA, okay, so we use a equation that's called eligibility index. And that equation used to cut off student reject or accept. But some people may say, this equation is not good. Maybe it's a better curve to accept or reject student by such a curve. Now maybe it's better, okay? Some people may say, this one is not good. Maybe this curve it may be better, okay? So to choose this curve or this curve or this curve, that require intelligence, okay? So you hear the word neural network, artificial intelligence, okay? So they are used to basically choose a better equation to find which region we should cut off, and that should find a certain curve that make a better decision to select the right group of the people right group of people to go to the San Jose State University. So that require intelligence. Okay, that require intelligence. So here I'm talking about different level of the data. Okay, so the data actually can be what? It can be physical phenomena. Okay, so that's in the real world. Okay, in the real world, here you have actually some bubble. It can be some raw data, so it becomes 760 SAT. Okay, and you clean some data, and actually, some student actually will ask for the rescoring or whatever. You clean up the data, then you actually send to the San Jose State's database to build a model. So the model keep learning. Over the year, they try different curve to decide which curve may select the better student, right? And every year, their eligibility index curve may be changing. Okay, so here, starting from here, this one's information, data. Okay, data, and after that, you actually have an eligibility index. Okay, that become your knowledge-based rules. Okay, so they will make decision based on those knowledge rules you learn over the year, and artificial intelligence is using machine learning to learn those past historical data to help you to process the whole thing to make a better decision. Is that okay so far? Hello, is that okay so far? Any question? Jason Lem, how are you? Is that okay so far?
Yeah.
Any question?
So,
no question?
no, not really.
Okay, so here I explain what is data science. Okay, so the whole data science is to collect data and do a lot of things. So now let's go back to the data itself. Okay, so data has two major types of the data. Okay, in our real world, we have two major types of the data. So data can be two types. Okay, two types. One is called qualitative. Okay, the other type is called quantitative. Okay, so quantitative like SAT 760. Okay, that actually is a quantitative data that we know. So quantitative data usually is that in your programming language you have integer, right? You have real number or double value. Okay, in Java it's called double, or these are quantitative, or a character. Okay, these are quantitative data. Qualitative data maybe is good, okay, bad, okay, super, okay, inferior. Okay, this kind of personal assessment usually is qualitative data. Okay, so this kind of data, both qualitative or quantitative, you will store in your file. Okay, so basically, let's pick the college admission process again. You fill in the Common App application form. There are some SAT score, right? There are some leadership. Okay, so some SAT score, this kind of information are more like a quantitative. Okay, leadership. No, can you use a leadership for number? Very hard, right? So you can only categorize them as what? International, right? And then national, right? And then state, right? State championship, and then maybe regional, right? Or maybe city, or maybe school. So they do not use a quantitative description, they use some sort of qualitative description. This is actually maybe the way they measure your honor or your leadership or your club experience. Is that okay? So your application material, after processing, you become number 760, okay, 555 AP score, okay, 4.3, okay, and then some sort of number of national medal 2, okay, whatever, those are numbers. And then some qualitative data as well. So your whole application profile will be processed like that. And then the whole thing go into some sort of holistic review, right? Holistic review. So they need to make decision, and decision need intelligence. So maybe this whole data can still be put into some AI program, and then they will learn over the year this type of the profile. The AI should pick up this student or should reject the student. Okay, is that okay so far? Is that okay so far? Okay, so data have two types. One is quantitative, one is qualitative. Okay, and that can all be described. So your programming language provide a string, provide a Boolean value, provide the integer, provide the double value, and those are helping you to store the different type of data in your computer. Okay, so now let's go back to binary. Okay, binary. So we are going to talk about binary. So we go back to the fundamental part of the what data being stored in computer. Okay, what data being stored in computer. So we start from transistor. Okay, we start from transistor. So a single transistor. Okay, a single transistor like this. Okay, so basically, if you look at the electronic field, you have the so-called NPN. Okay, N-doped semiconductor and P-doped semiconductor, and there is a metal oxide layer over here. Okay, the metal oxide here. So here you have a metal plate. So you charge, say positive charge being deposited to here. So you have a lot of positive charge over here, right? So you attract some electron to here, okay, and become a thin film, and then the negative electron will flow over here. So that become a transistor. So basically that would allow you to pass the data over there. Okay. So based on that, we design the transistor. Okay. We design the transistor. And because of the design of the transistor, we actually can design something like this. So this guy actually is called inverter. Okay. This one called inverter. So basically you have high voltage, say 5 volt input. Okay, high volt input, you will actually what? You will actually short it. This one will be shorted. This one will be open. So your charge stored over here will be discharged. So this will become 0 volt. Okay, if you apply high voltage on this side, and then if you have a low voltage on that side, say here we change it to low voltage. Low voltage. Let me use a blue color for low voltage. So that's a certain here you have 0 volt for low voltage. Then this one will be open, this one will be shorted. So it becomes charging here. So charging here, this one, the capacitor you charge it, it becomes 5 volt. So that becomes 1. So basically what I want to say is here, your data using this kind of digital gate will have 1 inverted to 0, 0 inverted to 1. This one we call it inverter. And logically is A, and this one is not A. Okay, is that okay? Is that okay? And then we also design something called NAND gate. Okay, NAND gate and the inverter. This one is NAND gate. Okay, NAND gate means that A, B, we have some logic here. So NAND gate is A, B. Okay. And 0, 0, 0, 1, 1, 0, 1, 1. So basically, this one we keep it 0, the other are 1. This one called named. Okay. And the inversion of it is end. Okay. So these two things, you got a C. C is the output of an AND gate. It will be 0, 0, 0, 1. That's your AND operator in Java. Oh, okay. So it will be the AND in your Python. Okay, so that one is called AND gate. So you have you can create the inverter for negation. You can create an AND gate or AND for AND operator. You can also create a OR gate. Okay, So this one actually is, I'm sorry, this one only single input. So here you have A input, you create a bar, okay? A, B, you create A and B. This one you have A, B, you create A or B. So this one is not and or. So this, based on these three basic functions, we build the whole logics of the computer, okay? And then all the computer being built based on these logics, okay? Based on these logics. So basically, what? This kind of electronic use binary data. Binary data, okay? So use binary data. So here we have this different gate. Let's look at a adder, single bit adder, okay? Adder. So adder, you have A input, you have B input. You will create a sum bit and a carry bit, okay? Sum bit and carry bit. So basically, you have one, or you will have 0 plus 0, you get 0. 0 plus 1, you get 1, okay? 1 plus 0, you get 0. 1 plus 1, you get 1, 1, okay? So this one's carry bit, okay? And if you have something called carry in, okay, carry in. Any question? Okay. So,
Can you go back to the 1 plus 0? Why does it say equals 0?
go to where? This one is 1. I'm sorry. This one's 1. Yeah. Thank you.
So can you? I don't really get the carry one. The carry sum.
The carry is the one you have 0 plus 1. You don't have carry. 1 plus 1, you're binary, so you become 1, carry 1 to the next bit.
Wait, but why do you have to carry 1 to the next bit?
You overflow this bit, you are using binary.
Okay, I think I get it.
Is that okay? So let's assume that actually, okay. So what I want to say here is like, okay, what I want to say here is like, we can have a full adder design. So you have carry in, and this one is carry out, okay? And you have a sum bit. You have A and B, okay? So basically, you will have possible A condition, okay? So A, B, C carry in, okay? So 0, 0, 0, 0, 0, I'm sorry. C in should be put over here, okay? So 0, 0, 0, let me actually clean it up, okay? So you may have a carry in. Carry bit in is the carry from the previous bit, okay? So, okay, let me finish it, okay? Let me finish before I talk about it. So you may have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, okay? And then 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, okay? So your sum bit and your carry out will be here, okay? Sum bit is actually 0, 1, okay? Let me change the order. Should be carry on the left side, sum on the right side, okay? So the sum here, okay? Sum here, carry bit here, okay? So you end up 0, 1, 1, 1, 0, okay? So 1, this one, 1, 0, 1, 0, 1, 1, okay? So here basically, this side should be 0, 0, 0, okay? Basically, the carry bit and the AB, you are counting how many 1 in there. So this is 1, 1, you get this. This one, 1, 1, you get this, okay? This, you have 2 of the 1, you get this, okay? Here you have only 1, you get only 1 here. Here you have 2, 1, you get this, okay? So what we can see right here is actually sum bit actually would be A equals or B equals or C. You get a sum bit, okay? You get a sum bit. So don't put it too complicated. Basically, the adder just can be designed by the inverter and the AND gate and the NOR gate. That's what I want to say. Okay, so the whole computing system can be designed by the transistor that we talked about so far. Okay, and the conclusion is all of these things use binary. Is okay? That's what I want to say. You don't need to remember all of these. Okay, they will not be tested. The whole thing is that the whole computer is using binary system because we build the whole computer industry based on the transistor, based on the 0 and 1. Is that okay? Hello, is that okay?
I'm sort of, I need to kind of, wait, so can you explain the C part? I'm really confused on how you got those digits.
This actually you have carry in, right? So carry in an AB, you are calculating the numbers, right? So basically say you have two number, right? Your two number, one is called A. Your A can be 0 or 1, right? Say 0. B can be 0 or 1. And you also have a carry in from the previous bit. So basically your sum bit is over here. Your carry out bit is the next one. So basically if A, B, C, they are totally 1, 1, 1, 1, 1, here you will get 1. If 0, 1, A, B, C, they are all 0, you'll get 0. Is that okay?
Yeah, but how does the carry? Oh, so the carry bit doesn't have anything to do with the addition of the A and B.
It has. Carry bit has. Yeah.
Wait, but how did you find the carry bit digit then?
Carry bit digit actually is the sum. So if you look at here, the left hand side you have 0, 0, 0. They are 0, right? So so right hand side here you have this one is 0. This one actually is 1. This one is 1. This one is 2. 1, 0 is 2. Is okay?
Okay, yeah.
You see it? So here you have 3. So here 1, 1 is 3. Binary 3. Is okay?
Well,
You have 1, 2, 3, 3, 3, 3, 1 here, right?
yeah.
And 1, 1 is 3. Is that okay?
Wait, but I just don't get how 1, 1 is 3.
How 1, 1 is 3. That's binary weighted.
Okay, all right.
That's binary weighted. So basically, this carry bit has a weight of 2. Okay, now let's actually look at the next one. Okay, this one, let me take a picture and then let me explain it later. Okay, so this one, let's take a picture right here. Okay, let's take a picture right here. Let me actually put into the chat. Okay, let me put into the chat. Actually, let me see from my computer. Okay, let me put the picture from the chat box. Okay. Let's look at the number system first before we actually come to explain this. It's a little bit too hard. I think right now it's a little bit too hard right now, okay? Okay, let me pause it. Okay, so the image is over there, okay? You can download the image. So now let's actually look at the number system. Okay, let's go back to the number system. So the number system, okay, number system. So we talk about 457, this number, okay? This one really means that 457, but it really means that 4 times 10 to the power 2 times 10 to the power 5 times 10 to the power 1 plus 7 times 10 to the power 0, right? This one we call it weight, right? So each digit you should have a place. So we call this one ones place, right? We call this one tens place. And this one we call it 100th place, right? And we also have the value. This is called value. So number system is built up by the place of value. So you have ones place with 7, tens place with 5, hundreds place with 4. This one we call it decimal system, and it actually is called 457. Is that okay? Is that okay? But if we look at the number, the real number 457 is 4 times 10 to the power 2 plus actually 5 times 10 to the power 1 plus 7. Is that okay? Any question here? So this one we call it value, the digits value, okay? And this one we call it place, right? Ones place, tens place, hundreds place. So our number system is actually built up by this the so-called value and place, okay? Value and place. Any questions so far? Hello, any questions so far? Hello, any questions so far? No? So no, let's actually go back. Okay, let's actually don't share, okay? Don't share, let me actually view speaker, okay? So let me actually see, I'm not, wait. Okay, so here, let me choose my view, okay? Sorry for that. Okay, how can I choose me? I should highlight spotlight for everyone. Okay, so here, okay, you can see my hand, right? So my hand, if I try to count, I try to count, right? So I try to count, some people use the Chinese way to count. So it's a 1, 2, 3, 4, 5, right? So 5 fingers, I count 5, and then maybe 6, and then maybe 7, right? And 8. And everybody awkward, you may only count up to 0 to 9, maybe. So that actually is very difficult to count with this one. But you can also use the binary system to count 1, 2, 3, right? And then 4, 5, 6, 7, and then this one 8, okay? And then 9. So you have to handle your finger, okay? 9, and then 10, okay? And then 11, and then 12, right? So basically, handling your finger right, you can actually have 5. Actually, you can have the totally 5 fingers that you can use, right? So you have your thumb, okay, your 5 finger. You can basically have this one 0 or 1, 0, this one 0 or 1, this one 0 or 1, this one 0 or 1, this one 0 or 1. You can count up, so you can have 5 bits. So you can represent 2 to the power 5 number of the symbol you can do. And it's actually starting from 0, 0, 0, 0, 0 up to 1, 1, 1, 1, right? And that is from 0 to 31. Is that okay? Is that okay so far? So what I want to say is, here, I use my hand. You can use 1. This one's on, right? The first bit is on. Off is 0, so this one's 0. So 1, and then 2. My second bit is 1, and first bit is 0. And 3, right? 3 is 1, 1, 1, 1. 4 is like this, right? 4, 1. So by doing that, you can count 1, 2, 3, 4, 5, 6, 7, and then fourth bit 8, right? And 9. Okay, then it becomes harder to count. Okay, but you can count to 31 if you really your finger is very good, okay, very flexible. So anyway, we started from 0. 0 is 0. Okay, so let's look at this one. We have single bit. We have 0. Okay, I'm sorry. We have 0. Okay, so if we have 0, we have 4 bit. 0 will be 0. 1 will be 1. 2 you carry 1 bit, so it become 1 0. Okay, 3 actually you continue to change this bit, so it become 1 1. 4 it become 1 0 0. Okay, 5 it become 1 0 1. Okay, 6 it become 1 1 0. 7 it become 1 1 1. 8 it become 1 0 0 0. 9 it become 1 0 0 1. 10 it become 1 0 1 0. Okay, 11 it become 1 0 1 1. 12 become 1 0. I'm sorry, 1 1 0 0. 13 it become 1 1 0 1. 14 it become 1 1 1 0. 15 it become 1 1 1 1. And we use all the 4 bits. Is that okay? Hello, is that okay? Any questions so far? Let's see. Catherine, are you okay?
Yeah.
Did you learn this in the class or no? Before in APC concept principle? Know it or no?
I don't think so.
You don't think so? Okay. Maybe some teacher didn't teach it. How about Michelle Wing? Have you learned this before or no?
Yeah.
Yeah? Okay. I just check, okay? But you need to learn this, okay? You need to learn this. You will be tested, okay? You will be tested. So now another thing, okay? Now that's it. Let me actually clean this out. This is called binary representation, okay? So binary representation. Okay, it looks like some students have not learned this yet, okay? So what is very important is this one called decimal, okay, binary, octal, and hexadecimal. You must learn this number system before you take the AP exam, okay? If you don't know about this, you cannot survive it, okay? So here, let me pick a simple one. Let me see. This one may be a good. This one is not good. Okay, this one's not good. Let me try a different one. This table may be better. Okay, let me see. Let me try to pick a good one. Okay, this one's good. Okay, this one's good. So let me copy this image. Okay. Also put in the checkbox. Okay. Wait, it cannot be pasted in this way. Sorry for that. Let me save it. Save the image to my logo and then upload. Okay. And then upload that image up. Okay. Yeah, haven't learned it. It's okay. We will review for you. Okay. So here you have the numbers. So this chart is very important. Okay, this chart is very important. Okay. So here you have 0, 1 to 15. Okay, and this one's decimal. Okay, so let's look at binary. So 0 will be 0, 1 will be 1. Okay, 2 you need to carry 1 bit to the next one. Okay, 2 you need to carry to the next one. 3 you actually put another 1 over here. Okay, so let's look at this one. Let's look at 3. So 3 would be 1 times 2 to the power 1 plus 1 times 2 to the power 0. Is that okay? Is that okay? So let's assume that we have 13. 13 on decimal is actually 1 times 10 to the power 1 plus 3. That's called 13. If we look at this one called 8, this 8 actually is 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 0 times 2 to the power 1 plus 0 times 2 to the power 0. So that's the number system we talk about. Any questions so far? Any questions so far? I see Sunny Yen. Is that okay so far?
Yeah.
Okay. Have you done this before?
Yeah.
Okay, you know it. Good. So these are very important. Okay, so the number system. So what we get started is the decimal system. Okay, decimal system is 457. It actually is 4 times 10 to the power 2 plus 5 times 10 to the power 1 plus 7. Okay, it's actually using 10 as base. So if we have 1101, this one binary, if you use a binary system, it would be 1 times 2 to the power 3 plus 1 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1. So that guy is actually A plus 4 plus 1. It is 13. Okay? Decimals are 13. Any question? So we can call decimal as base 10. Okay. This number we can call it base. We can also call it radix. Okay. This number we can call it base 2. It's base, or you can call it radix is 2. Any questions so far? Any questions so far? Is that okay? Anybody not comfortable with it, let me know, okay? How about Ryan Wu? Are you okay?
Yeah, I'm fine.
Okay. Next one, I will have a question. Now, let's do this one, okay? This one is important, like, okay, let's actually look at 57. How to convert 57 to binary. Let's use a smaller number. This one too big. Let's use 13. Okay, let's use this number 13. How to convert 13 to binary? Okay. So this one let's actually do 13 divided by 2. Okay. 13 divided by 2, it will be what? 6 remainder 1. So that the remainder put over here. Okay, so you do 13 divided by 2 is 6, 12, remainder 1. So this one, put it over here. This one, put it over here. Okay. So that's the number we put over here. Okay. So now let's continue. This one actually we divide by 2 again. It is 3 remainder 0. Divide by 2 again. It will be 1 remainder 1. So we read it from here to here. It becomes 1101. And this is the binaries representing for 13. Is that okay? 13 decimal will be equals this. So will this be tested in AP concept principle? Yes. You need to be able to convert from decimal to binary, also to hexadecimal, also maybe octal. Is that okay? So at this moment, let's just looking at these 3, decimal, binary, and hexadecimal. So far, okay? Any question? You can do this to get it, okay? Any questions so far? So let's look at one number, okay? Let's look at one number here. Can somebody tell me that, okay, let's have some number like 97. 97, can somebody type to the checkbox of the binary value for this. Is that okay? You try to calculate and then you type to the checkbox. Is that okay? Try it now. 97 converted to binary. You type your binary code and then your name. Okay, so I will know you. It's you. So somebody doesn't type, I know that you doesn't know, maybe. So try your best, okay? Any question here? Let me try the 13 one more time, okay? 13, you have the 13, you divide by 2, you have 6, remainder 1, right? Divide by 2, you have 3, remainder 0. You divide by 2, you have 1, remainder 1. And you read from here to here, okay? So it becomes 1, 1, 0, 1. Can anybody try? Everybody try? Type to the checkbox. So I know you know. I would know that you know about how to convert 97 to binary. This one will be tested, okay? Okay, I could see 2 students submit the answer, okay? Okay, this is not a test, okay? This one just to make sure you understand it, okay? Make sure you understand it. Okay, good. So this one actually is the conversion from decimal to binary. Okay, let's do it on the reverse operation. Reverse operation, if you have 1101, you are trying to convert to decimal, then you put a weight on it. So 1, 2 to the power 1, okay, 2 to the power 2, 2 to the power 3. Okay, so I'll rewrite it as 1, 2, 4, 8. Okay, instead of using 1 in the power format. So it will be 1, 2, 4, 8. Okay, you times. So that will become 1 plus 0 plus 4 plus 8. So that you will get 13. Okay, this one is from binary, you convert it to decimal. Okay, convert it to decimal. So now we know this one is easier. Okay, I think this one is easier. So now we actually know how to convert from decimal, okay, to binary. Now, if we want to convert from decimal to hexadecimal, so hexadecimal is actually base 16, okay, base 16. So let's assume that we still have the 97, okay. So this 97, we are going to convert it to base 16. So you divide by 16, okay, divide by 16. Divide by 16, you should have 6 remainder 1. So you'll be 6, 1 hexadecimal. Is that okay? You'll be 6, 1 hexadecimal. So that would be 6 times 16 to the power 1 plus 1. Is that okay? Any question? Any questions so far? Any questions so far? No question? And Nathan, are you okay?
Yeah, I'm fine.
Okay, so this one is converted to 16. So converting to 2, you use a 2 over here, okay? Converting to base 16, you actually use a 16 over there, okay? So that's not hard. The same method can be used for any base to do conversion, okay? So here, this one is the way we convert it to hexadecimal, okay? So that's the way we convert it to hexadecimal. And you must know about how to do conversion between your base 10, base 2, and also base 16 and base 8, okay? Base 8. Okay, you must know about this. And also this one, you have the 97, you convert it to base 16, it becomes 6 and 1, right? 6 and 1 actually, it becomes 6 and 1, right? It becomes 6 and 1, but basically this one, if I convert it to binary, I will actually convert it to base 16, it will be easier. Because 6, you have 1, 1, 0. 1 in hexadecimal is actually 0, 0, 0, 1. So you can directly get this without using 97 divided by 2 and then perform long division, very, very long division. You can use a convert it to hexadecimal, right? And every 4 digits of them, every hexadecimal number will be converted to 4 bits. Is that okay? Is that okay? Hello, is that okay? Any question? You must know about this, okay? This one actually is tested. When are we going to use this? When are we going to use this one? And it will be tested, okay? It will be tested. So when are we going to use the list number conversion? Let's actually look at the color picker, okay? Color picker. So we have the color picker here. We have the color. So here we have the RGB, right? We have RGB. So RGB here, if we want to convert our RGB to hexadecimal code. Okay, convert from RGB to hexadecimal code. How can we do it? Okay, it's very quick. You have 50 divided by 16. You get 3. Okay, remainder 2. Why? This one actually is the first 2 digits. Is that okay? First 2 digits in hexadecimal code. Is that okay? Hello, is that okay? Alex, is that okay? So here you have RGB is red, green, and blue. Okay, I'm sorry, I actually changed it. Okay, sorry. Okay, here we have a color. Okay, I'm sorry, I actually kind of screw up. I touched the color. So anyway, so here we have BA, right? Second one, BA. Let's look at BA, and this one 68. 186. 186 divided by 16, it will become 11 remainder 10. 11 remainder 10, you get 3 and 8 in hexadecimal. Is that okay? Nico, are you okay so far?
Yeah.
So these will be tested, okay, in the color conversion. Some problem will need you to do this, okay? And remember that, okay, when you go over the 10, you need to use ABC to represent in the hexadecimal number, okay? Okay, so let me actually go back, okay? So maybe this number system, you need to study this, okay? Some student may need to study this number system, this portion, okay? It had more description on here. Let me post it in the chat, okay? Let me post the reading sense in here. So that is one topic you need to know, okay? In the regular year, you should pick up this one. That's the binary system, okay? That's the binary system. And you also need to learn how to convert it to hexadecimal. So data is represented in the binary format in computer, okay? And our human being like the decimal value, okay? Our human being likes decimal value. So the bit, the so-called bit, is originally from the binary digit. So a digit actually is a place, okay? A place in the number system is called a digit, okay? So 457, this is 7 by itself is called a digit. 5 is a digit, 4 is also a digit, okay? So binary digit is the digit that say 101, 1101 for 13, okay? So any one of these is actually is a binary digit. So binary digit, we call it bit, okay, we call it bit, okay, BIT, binary digit, okay, that's called binary digit. And a bit, we call it a byte, we call it a byte. So originally a bit, okay, originally a bit, we call it BITES. But it's too much like byting, okay? Too much like byting, so they change, okay? They change the I to Y to become byte, okay? Is that okay? Is that okay? So 8-bit, we call it byte. Any questions so far? About Kesselin, are you okay?
Yeah.
Okay, so 8-bit is a byte. Okay, 8-bit is a byte. And what does a byte is used for? A byte you can actually use to store your symbols. So there's something called Ascii code, okay? So there's something called Ascii code you need to know. So Ascii code is a table. It's a table, okay? It's a table right here. You actually see that it's a Ascii code. So here, for example, like here, the middle min, okay? The middle min. So for example, like A, okay, let's you look at uppercase A. Uppercase A, if you send email to your friend, okay? If you send your email to your friend, you do not send the image like A to your friend. No, you don't. You actually send this binary code to it. And this binary code is 0, 1, 0, 0, and 0, 0, 0, 1. It is hexadecimal 41. It is decimal 65. So ASCII code is a code that is called American Standard Code for Information Interexchange. Okay, that's called ASCII code. American Standard Code for Information Exchange. So you write email, you do not send out a image to your friend or font to your friend. No, you really just send 1 byte like this to your friend. Okay, you send E, you will send this byte to your friend. Is that okay? So when your data stored in the computer as a string or character, it is using the so-called ASCII code set. Okay, that's initially only English. You use this kind of ASCII code to send it, but later people find out this may not be enough. For example, like Chinese letter cannot be put into there. So they invented another set of the code called Unicode. Okay, so they invented a Unicode, so you actually what? You can send not only the Chinese letter, but also the so-called symbols or emoji to your friend. Okay, So here say my last name. My last name is actually Unicode. Okay, Unicode 5468. So Unicode 546 Unicode 5468 is my Unicode, my Chinese name, last name. Is that okay? This means what? Means that when people write email with my last name, it will send out what? 5. 5 is what? 0101, 01, right? 4 is 0100, okay? 6 is 0110, 8 is 1000. So it will actually send a 16-bit of these to their friend. Is that okay? This one is called Unicode. So English use Ascii code. And then other language prefer to use this Unicode. Is that okay? Any question? Is that okay? So that tells you what the symbol being stored in the computer. Okay, I tell you what symbol being stored in the computer. Okay, so this AP concept principle actually is to teach you what number being used in the computer and what are the use of the bits over there. Okay, so these actually are very important. Let me go through the slices. Okay, so basically you have the bits, okay, and digits. And then you have the number base. So number base can be 2 base, can be 10 base, can be hexadecimal 16 base, can be 8 base. Okay. So in the computer, in the real computer, we use machine code. So machine code is basically using the binary system. Only 0 or 1 being used over there. Okay. Only 0 or 1 being used over there. So binary system use only the combination of 0, 1 to represent the value. Okay. And can be very little difficult, can be a little difficult to understand it. Okay. So now if we think back to the elementary school, we'll remember the place and value system. So basically it's similar to the place and value system. Okay. So here you have this one, you have place and value. Okay. So that's a decimal value. And you binary use, you use the place of the based on 2's place. Okay, the weight is actually power of 2. Okay, so each binary digit we call it bit, and a bit we call it a byte. Okay, we call it a byte. A byte originally is actually from bit. It actually originally from bit. Okay, but it's too many, so we change it up. It's similar to byte. It's similar, it originally was byte, so it changed to BY, okay. But it is a bit. But for foreign language, we actually use what? We use the Unicode for it, okay. So hexadecimal is used because what? Because say you have my Chinese letter, okay, my actually last name. Yes, question?
Yeah. So for the exam, do you just need to know how to convert binaries to decimals, binaries to octas, and like binaries to hexadecimals? Or you also have to know how to like convert hexadecimals to decimals and decimals to hexadecimals and all of that?
Yeah, you all. Okay. You all need that, yes. You all need that, yes. Okay. Okay, anyway, so here actually you only all those. You will see them in the practice exam, okay? Pretty soon you will see them in the practice exam, okay? So here we actually will convert the later translator into some hexadecimal representation. Hexadecimal representation exists because you have 5, 4, 6, 8, okay? So this one actually is hexadecimal, so it says 16 base. But if I write into this format, if I write into binary format, 0, 1, 0, 1, okay, and then 0, 1, 0, 0, okay. So actually, it's very difficult for you to read, okay, very difficult for you to read. That's a real format that computer recognize, but very difficult to read. So usually, when people need to represent it into some sort of a code, they use a hexadecimal, okay? They use hexadecimal. So that's why actually when you actually look at the color picker, okay? So let's go back to color picker. So color picker, when you go back to the color picker, you need to pick a color. You actually, this color picker, they use a hexadecimal code. You can use this one to paint your color, okay? You can use this one to paint your color, okay? So usually when we use what? When we use like Copan, okay, Copan, we try to use a JavaScript, okay? We try to use a JavaScript. So here, let me log in, okay? So I try some of the code before, okay? So here, let me see, let me try look at it, okay? So let me try different project. Okay, let me try different project, some different project. So here, let me use this one, Watermelon 11, okay? So let me bring up my CSS, okay? Okay, let me bring up the CSS. So this portion, you can see the background, they have color. So this background, if I change the background color, okay? If I change the background color to, from this color picker, I pick this hexadecimal code. Compared to here, I put it over here, and I save, it change color, okay? Do you see that? Is it okay? I can run the program, but actually the background color being changed. Let me try one more, okay? So here, let me actually choose a different color, okay? Say this color. And color, I copy this hexadecimal code, okay? Go back to here, let me actually put it over here, okay? And it changes the background color. So basically, hexadecimal code is widely used in computer science, especially for the color, okay? When you design some website, okay? Any questions so far? So here, Ascii Code, will they test it? Yes, they will test it, but they will test you by the number of bytes, okay? Number of bytes, okay? So usually color representation will need the hexadecimal, okay? So abstraction, we talk about it. From the physical data, you actually abstract to the symbols. That's actually abstraction. So abstraction is a process of reducing the complexity by using a simpler concept or simpler symbol to represent it. Okay. So from your 5 stone to a number 5, that's actually abstraction. Okay. From you write a maximum number function with xy, okay, and then you write if actually x greater than y, you return x, okay, else you return y. You write a function that's also abstraction, okay. You write a function that's also abstraction. So this one is abstraction, okay. So next one is analog data and bit representation, okay. So we talk about the number system, and our real number or integer number will be represented in the binary format. So that's the one we first talk about. You'll be the number system, okay, binary number system. Our symbols, we will use the ASCII code or Unicode to represent them, okay. So our data may be qualitative or quantitative. They will be represented in different format, okay, will be represented in different format. Now, next one, we talk about the sampling, okay. Sampling, we have analog data and bit representation. So analog data is data that measure continuously, okay? Continuously, that you have analog data value changing smoothly. So analog data is the real world data, right? So for example, today's temperature. So today's temperature will not be, say 65, and will not be 65 all the way, right? It will not be. So the temperature for today, it should be up and down, up and down, up and down, okay? So maybe high 72, low 63, average maybe 68, something like that, right? So if you measure at every time, we call it sampling. So sampling is actually you try to measure the data, okay? You measure data, and that's a continuous value. You try to sample it and convert it to digital. That's called sampling, okay? It's called sampling. So sampling actually is conversion of your analog data to digital. And in digital format, you can store it. You can store it, okay? So you can store it. So you use a thermometer to measure the temperature, okay? Degree C or degree F, this one actually different system, but they all do sampling, okay? They all do sampling. And then you need to represent the data into bits, okay? Then you need to represent the data into bits. So here, you are doing some sort of, doing some sort of quantization, okay? So your analog signal will be sampled at different time, and it will actually be put into digital. So basically, there are different ways to do sample, okay? You can use the pure analog signal. You can use a sampling over time. So this one is discrete sampling, okay? And that's a discrete time, okay? And you can also use a continuous time but discrete value. And you can also use all digital. So nowadays, when we talk about digital, it's all digital. Time domain digital, value domain is also digital, okay? We talk about this one, it's actually digital domain, okay? So basically, that's the way we actually convert data, okay? So sampling is to convert your signal from analog data to digital data, okay? So that's called sampling technique, okay? So digital data must be formatted in a finite set of possible values. So usually you convert it back to 8-bit, okay, or convert it to 16-bit. So let's look at what is sampling in real world, okay? So what is sampling in real world, such as we actually use this one called audacity, okay? So let's look at this audacity, and here, okay, here I'm trying to recording my own sound, okay? So let's see. Hello, 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 how are you? This is Dr. Chow, okay? Thank you, bye-bye. Okay, so this one is called sampling, okay, sampling. So let's actually zoom in the data a little bit, okay? Let's zoom in a little bit. Hello, how are you? Hello, how are you? Okay, this is Dr. Chow. So this one is actually called sampling, okay? So you sample the data, but you actually can continue to zoom in, okay? So you zoom in, you will see that, okay, my voice like this, okay? My voice like this. So this one is actually what? Using sampling. But this sampling, they have a sampling rate. So when I do sampling rate, here is a rate, okay? Project rate is a 44 kHz, okay? 44 kHz to do sampling. And when it's stored to the computer, when you store it to the computer, we say export audio. You will use a what? 16-bit PCM. 16-bit means that each voice sample we use a 16-bit data to store it. Is that okay? Hello, is that okay? Any question? Hi, any question? So this one is the so-called sampling, okay? Sampling your image taken by video or your audio taken by this speech recording devices. They would all sample the data into digital format, okay? They will all sample it in digital format. So sampling can be a digital reader for the temperature, can be this kind of the recording device, okay? They keep do sampling every day, okay? But there is certain range. Say I use a 16-bit, there must be some bit that I cannot represent, okay? So say here I use 16-bit, but my maximum range that I can recall, there may be some certain level. It will overflow my bit. So my 16-bit range, I can only recall in this region. So any volume above it or below it, I may not be able to sample it, okay? So I may, my signal may be charmed in this way, maybe charmed in this way. My real signal may be charmed in this way because of the number of bits, okay? Because of the number of bit repetition. That is called overflow error. Is that okay? That's called overflow error. So overflow error happen when what? When your quantizer actually range is not enough. Your quantizer range is not enough, you will have the overflow error. There's another type of error called quantization effect. Quantization effect happen in this case, okay? You only have a label, right? So you are represent 0 to 7, but somehow your signal may be 5.25442. Then you will lose some detail because you can only recall 0 to 7, and those detail will be dropped. Those kind of things, we call it quantization, okay? We call it quantization. So quantization error is the red one is a quantization error, okay? You will still lose some bits when you do quantization. You try to recall your digital audio. So actually, when I use the Audacity to record my voice, the voice cannot be 100% as my original one because there's quantization error. So it cannot be 100% the same. But digital one has a good thing is like, after you record, it becomes digital. So no more distortion, okay, no more distortion. All the day we use the tape, audio tape, or we use a video tape, and it's storing the analog data, and analog data, after many years, the signal quality will drop, okay? You actually will lose the signal level, okay? So this one is the sampling. So sampling basically is to convert your analog data to digital, okay? And they may be overflow error, there may be quantization error, okay? Both the quantization error and the overflow error will be tested in the exam, okay? You must know about the concept. So the number system. So the number system we talk about, it can be base and to the power something. So it can be 10 base, it can be 2 base, you can be 5 base. Okay, so this is what we talk about it. You can use a polynomial evaluation to get the 547's real value in decimal system. Okay, you put a base 10 to that, you got a polynomial evaluation. So here, if you have 1101, 1001, you convert it to binary. I'm sorry, convert it back to decimal. You put a weight under it. Okay, 1 times 1, 0 times 2, 0 times 4, 1 times 8. Okay, something like that. You sum them up, you get your decimal value. Okay, and when you do the conversion from binary to decimal to binary, you do use this method called successive division, okay? Keep dividing, okay? So divide your quotient put here, remainder put here, quotient put here, remainder put here. And then at the end, you read from here to here, okay? That's called successive division. And you need to know about decimal to binary conversion, binary to decimal conversion. Also this table very important. How to convert in different number system, okay? So now we finish the binary representation, okay? Let's look at the file type. Now we are actually 10:30, okay? Let's have a break, okay? Let's have a break and we will go back and continue to work on the file system. Is that okay? Let's have 5 minutes break, okay? Is that okay? So come back on 10:35, okay? Hello, hear me? Hi, Alex, hear me?
Yeah.
Okay, sure, okay? We will get started again. Okay, the byte and bits are very important, okay? Byte and bits are very important and you need to know about the concept and know about how to convert it. Okay, next one important here is you must know about the order of magnitude, okay? So you need to remember you have 1, okay, 2, okay, up to 2 to the power 16, the number you need to remember, okay? Next one is 2 to the power 10 equals, okay, 1024, okay? Sometimes we call this one 1K, okay? Because it's very close to 10 to the power 3, okay? So remember every 10 bit, it's a little bit like 1,000, okay? So 2 to the power 20 would be equals to 1 mega. It's a 10 to the power 6, okay? That's a megabyte. So usually we use this one, 20 bit, to talk about 1 megabyte, okay? 20 bit of the address, we talk about 1 megabyte. So 2 to the power 30, we call it 1 giga, okay? It actually is 10 to the power 9, okay? Roughly, it's not exactly the same. And then 10 to the power 2 to the power 40, we call it terabyte, okay? So that's the measurement of the storage, okay? Measurement of, it's not exactly the same. 2 to the power 10, it's not the same as 10 to raised to the power 3, okay? Not exactly the same, but sometimes we call it equivalent, okay? So when you measure your hard disk, it's same like this. So this is the unit for the storage, okay? And that's one way to look at it. And another way we look at the data would be you from bit by data field, and then object, and then data structure, and then file, and then package, and then database. So this is from the function or the data organization of your file, okay? So you have different file type, you have text type, you have AVI type, you have JPEG, you have WAV, you have different file type, okay? So the first one, text. So text is data representation. You store your email in text. So we use the Ascii code or use the Unicode to store your data. So this one is fine. Okay, that's a data representation. String is used to store your text. Okay, so you have the string. This one's easy. Okay, so here one thing is like, okay, one thing is like here in our computer. Okay, in our computer. So right here. Right here, if I actually create a file, okay, let me create a file. Okay, so here let me use a lecture 2, okay. So right here, if I actually create a text file, okay, so this one, text file, let me call it hello, okay. So this one, let me call it hello, and actually I open this one in editor, okay. And here I type in hello, okay, and I save. Okay, I get out. So now I use the Microsoft Word and I create a same file called hello, okay? And I actually open it. Okay, coming up, okay? So I also type in hello, okay? And I actually also save. Okay, so these two files actually what? The text file is actually 1K, but the Word file is 12K. Why is that? Okay, this question for Nico. Why, if I save as a text file, it actually only 1K? And actually, I only store hello in there. Why it's actually taking 1K? And hello, I actually also save in Word file, but it takes 12K to store it. Why is that? Hi, Nico, hear me?
Because it reduced the size.
Number one, I only type hello. There are only 5 data, right? 5 data is supposed to be 5 bytes or 10 bytes, right? How comes it take 1K? The answer is the minimum unit of the file in the Windows now is actually using 1K. So 1K is the minimum size for a file. Is that okay? 1K is the minimum file for the size. And second answer is that why Word file is actually way bigger than the text file. That's because the Word file, you need to store the file format, okay? Say your font, your color, your background color, a lot of things need to be stored into Word, but your text file doesn't have the information, okay? So that's why these two files have the size are different. That's why these two files are of different size, okay? So this one is text file. Text file, we only talk about this. Next one is the image, okay? So image, you have different kind of image, okay? One is called black and white image. So black and white image, you store 0 and 1 on each bit, okay? On each bit. So here we have the image. So a few things you must know about is actually the image, okay? Image is a type of data store graphic or pictures, okay? And then second word is actually called metadata. So metadata is very important. Metadata actually every time the AP will test it many times. So metadata is data about data, okay? Metadata is actually data about the data. What does this mean, okay? What does it mean? So say I have an image file, okay? So I have an image file. So this image file, suppose I have a JPEG file, taking picture, I have a JPEG file, right? So this JPEG file, suppose I have a person over here, right? But in fact, in addition to the content, I also have a section that actually store my metadata, okay? So the metadata actually say you including file size, okay? Day of the picture being taken, author, okay? There are several things called metadata will be stored into the file. So it's actually nothing to do with the content, only related to the data of the file, okay? So where can I see this metadata? Go back to my Audacity, okay? Go back to my Audacity, actually right here, if I actually do export audio, okay? So right here, let me actually go up, okay? Go up, and then let me put into this one, okay? Put into lecture 2. That's save as A, okay? So when I save it, you will ask me something like artistic name, track title, open title, and then genre and comment. These are the metadata. Is that okay? These are the metadata. So right here, if I fill in the author, so the author is, let's assume that it's me, actually Eric Chow, okay? Is that okay? So open title is entertainment. These are called metadata. Is that okay? So data about this file. So later people look at this audio, they will know that who created this file and what is the open. But the content is different from here. So this metadata is a header, some sort of a header adding to your audio file, talking about the author, who is the author, okay? And what's the title? And your real signal is after it. Your audio signal is after it. Okay. Ascii, is that okay so far?
Yeah.
Okay. So you will see some problem that is in your exam. Okay, you will see that. Okay, we later will try. Okay, we'll try to answer problem. You'll see what is metadata. So metadata is data about data. Okay, so each picture has some pixel. Pixel is actually called picture element. Okay, pixel is called picture element. So here we have a pixel. Pixel is actually originally called picture element. Picture, P-I-X, okay, an element. So it's called pixel. Pixel is a bit, a single pixel. A single pixel may have RGB, red, green, and blue, and also a alpha channel. Okay, alpha channel for its transparency. So basically, it may have each one 8-bit. So one pixel usually store as 32-bit. Okay, 32-bit. So that actually is pixel element. So you have a pixel. Okay, so right here it's okay. So that's you can store as black and white. If you store in black and white, each pixel has only 1 bit. If you store as black and white, each pixel has only 1 bit. Okay. If you store in color, it's a 32-bit. Okay. But you can also use the halftone to store it. So halftone look like this. Is using pattern to store your image. Okay, that's called halftone. So there's a black and white and halftone. You can also use halftone to store it. So your picture quality actually have a few different levels. Your picture quality have black and white. Okay, also may have halftone. Halftone is actually using pattern. Okay, and may also have gray label. Gray label is full scale gray label, and then may have color. Okay, may have color. These are different picture qualities. Okay, so here that's okay. That's actually this one. Okay, this one. Okay. So you can edit the different pixel. Okay, that's actually go a little bit faster. So these are the okay, so here that jump to this metadata. Okay, jump to this metadata. So metadata is data about data. Okay, so it actually metadata is actually it may have the descriptive metadata. It may have structural data metadata. It may have administrative metadata. Okay, so several things, but it usually is like this. You have your JPEG file, image file. Okay, may have file name, directory, file type, file size, and rating, title. Okay, a lot of things, and size, version. Okay, exposure, and different things, and these are called metadata. So you send a JPEG to the other person, he will look at the metadata and determine how to decode your JPEG file. Okay, how to decode your JPEG file. So here we have many different type of metadata. So you can look at it. Okay, you can look at it. So let's look at HTML. HTML also have some metadata. Okay, HTML also have some metadata, and you can use the metadata to determine what kind of code you will actually do decode. Okay, so here let's try to create a HTML file. Okay. Okay, so let's actually look at, if I try to create HTML, but let's call it a.html. Okay, so here we have an HTML file, and here we have this. Okay, create an HTML file. So here I just want to try to use, I have the body, okay, and I have body, so I will put my text over here, and I also have header. So usually you will put the metadata in the header portion. Okay, so right here I'm going to copy some Chinese letter in. Okay. Let me get it, okay. So these are some little kids reader in ancient Chinese, okay. So let me copy a few word over, okay. So let me just copy this portion, okay, just copy this portion. And then put into my file here, okay, so in my body, okay, in my body. So here, these are Chinese letters, okay. So now if I will use the metadata to make the difference, okay. So right here, let's look at it. If we use the character set equals UTF-8, okay, so let's actually use that, okay, use that. So let's put it over here, okay. So we have the so-called meta, okay. So metadata character set, okay, equals UTF, okay, 8, okay, something like this. And let me push it a little bit in, okay. So right here, I actually save, okay, save the file. And let me go back to the location, okay. So here is a file, I opened it. So it actually is some sort of Chinese letter over here, okay. So let me change the UTF-8. So I don't use the UTF-8, okay. If I use the HTML, okay, character set, okay, ISO, okay, 1889, okay, let me see. This one, okay, let me use this one, ISO 5, this one, let me use this one, okay, using ISO 8859, okay. So let me use this ISO 8859, okay, instead of UTF-8. Okay, let me use this one, save, okay. So the same file I open again, I cannot read it. I cannot read it. Because of what? The metadata tell the browser to interpret it using English. Okay, using English. So this Chinese letter become this. So cannot be recognized. So this one, if I actually comment it out, okay, if I comment it out, okay, let me actually put back the Chinese letter again, the UTF-8, the Unicode, okay, 8-bit Unicode format. Okay, so let me put back the UTF-8 again. Okay, put this one back. So save it one more time. This time let me reload it. It becomes Chinese again. So this one told you what? Metadata tell the browser what character set I'm using. So how the browser should interpret it. Okay. So when you send email, when you send JPEG, you send a lot of things. There are always some metadata that accompany your content to there. If you do not describe it in the right way, the decoder may decode it in different way, and you may not be able to see the right type of data you want. Is that okay? Any question? In addition to that, you may have some keyword or author or something that has nothing to do with the decoding, okay? So it's actually machine parsable, okay, machine parsable. So this one, okay. Next one, we talk about roundness encoding. Roundness encoding is like when we try to compress the data, your original data may be like this. You can write it down into white, black. So white, black, you can encode it in this way, okay? So for some images such as the fax machine, okay, fax machine, you write some data on it, okay? A lot of spaces are white. This roundness encoding may help to reduce the size of the file, okay? So roundness encoding is a simple way to do lossless data compression, okay? It's a one way to do lossless data compression. So image, we may need to use a data compression. So JPEG, in fact, is a compressed data format, okay? JPEG is a compressed data format. And we'll talk about the compression later, okay? So this one, you can use the YCB to do compression. So this one is the Jpeg Compressions algorithm. Okay, so we kind of jump faster. Okay, this one we kind of jump faster. Color image. So color image we use a hexadecimal. Okay, you have pixel, you have RGB. So this one okay. Favicon we bypass it. This is some term for website. So you may use the RGB format or CMYK format in the printer and monitor. These are different systems, and you have a color space. So this one okay. This portion okay. So that's about the image. Okay. Next one we talk about video. So video is a format that you store the movie or some animation, okay, or some animation. So video is a collection of pictures, okay. Say maybe 30 frames per second or 60 frames per second. So each frame is a picture, okay. But because that you actually video is actually has a lot of data, so you may need to use a compression. So each one of them is actually a JPEG format picture, but you may need to look into the interframe data dependency and do compression. So then you compress them into MPEG format. Okay, you can compress them into MPEG format. So that's the video. Okay, that's a video. So video usually you actually compress from the different image. Okay, we will talk about a compression scheme later. Okay, so video is used to store your movie or animation. Okay, audio is the one that we use for this Audacity. Okay, Audacity is recording my audio signal. Okay, so these few terms might be you need to know. Okay, these few terms you need to know is what is audio. Okay, what is audio and what is speech. These different terms you need to learn. So you have audio. Audio is sound, especially when recorded. Okay, audio and sound are different things. So sound is the vibration that actually travel in the air. So sound is the physical world thing. Okay, audio means that you record it. So audio actually is your sample result. That's called audio. Okay, humans audio is called speech. So speech is one kind of audio. Okay, audio usually is talking about the recorded format of the sound. Okay, recorded format of the sound. And frequency. Okay, you need to know about frequency, amplitude, period, and wavelengths. Okay, these few terms, let's actually look at a chart. Okay, so this chart is very important. Okay, you must remember this is a sine chart. Okay, so there's a term called frequency, there's a term called wavelength, there's a term called period, there's a term called amplitude, there's a term called speed. Okay, so amplitude means half of the peak to peak. This one we call it peak to peak. Okay, half of the peak to peak we call it the amplitude. Okay, suppose this is a sine wave. This is a sine wave. So A sine theta. This A is called amplitude. Okay, this A is called amplitude. So this A sine theta, you can write it down as A sine theta, can be written down as A sine omega t. Omega is angular speed. You can be written down as A sine 2 pi ft. F is the frequency. Okay, and then you can also write it down as A sine 2 pi t over t. This big T is period. Okay, this T is period. Okay, so F is frequency. So F equals 1 over T. Okay, T is period. F is frequency. Okay, A is amplitude. Okay, so that's that. Okay, and speed, okay, speed and wavelength. Your speed of the audio, okay, your velocity equals your frequency times lambda. Lambda is your wavelength, okay. Lambda is your wavelength. That means that within a second, how far your audio will go. And audio usually is transmitting about 300 something meter per second, okay. That's your audio speed, okay. But roughly you need to remember this different term, okay. Here we have a slide talking about it, okay. Higher frequency means that it's actually going faster, vibrating faster, okay, and the pitch is higher. Lower frequency actually is the pitch is lower, okay. So this difference thing you need to know, okay. Okay, one thing you need to know is this abusing, okay. In the exam, what's more important is a few words you need to know. There's a term called bandwidth. Okay, bandwidth you must know. Bandwidth is, say, you are transmitting using the Wi-Fi. Okay, so Wi-Fi have a bandwidth, say 100 megabit per second. So that's the maximum amount of the data that Wi-Fi can transmit. That's called bandwidth. Okay, and the real data that you transmit over the Wi-Fi channel, that's called data rate. Okay, so data rate always is below your bandwidth. You cannot go over the maximum data rate that you can allow by the Wi-Fi channel. Okay, so these two terms you must remember. One is called data rate, the other one is called bandwidth. Okay, so data rate is calculated by the number of bits you transmit over the channel. Okay, so say you have the audio signal, you need to use the number of channel times the sample rate times the time times the number of bytes. That would be the total file size. Okay, that's the total file size. And you can use the different frequency to calculate the byte, okay? And these are uncompressed data. So if you do not do compression, that is the file size you need to transmit, okay? And that will actually take a certain part of the bandwidth, okay? So that's that. And we have different file format for the audio. So this one is okay. So you can use the Audacity to record it, okay? Okay, so Audacity is a tool to help you to process the different digital format, trimming, slicing, assembly, okay, different function. Okay, here we omit abusing. Video, you have abusing, you need to remember. One is resolution, okay. Resolution is your image size, okay, different image size. So when we have the high definition, that actually is 1280 times 720, okay. This one actually is 2 megapixel image, is 1920 times 1080. So sometimes you buy TV, they'll tell you is 1080p. P is progress scan, okay. 1080i, that's actually interlace, okay. So that's one term you need to know. Codec is coder decoder, okay. So your data impact from the sender to the receiver, you need to encode and then decode. Let's use coder, okay. Bit rate is the number of bits being transmitted, okay. Bit rate is the number of bits being transmitted. Frame rate is the number of frames sent by the video per second, okay. That's called frame rate. So here originally we have analog TV, you use the cathode gun to shoot out the electron to the pixel, and then you use the scan line. Okay, this is the old day. And your digital TV use a progressive scan or interlace. So progressive scan means that you every frame you scan every pixel. Okay, that's called progressive scan. Interlace means that first image I scan this portion. Okay, second image I only scan the even number row. Okay, so that's a different. So your picture size for your TV grow over the year with different size. Okay. So this one, okay, this different size, we just keep, okay. So here we have different, this one, okay, we don't work on this, okay. Video streaming. So video streaming, you basically need to have a recorder. You take the video, okay, and you upload to the computer system, okay, and you do, and then the player actually go to the website and download the video back, okay. So basically, this one is the so-called video streaming. So right now, actually, we are using Zoom, right? We are using Zoom. So say basically for me, I'm sitting here, right? I'm sitting here. So I take my audio and video, I transmit to Zoom, right? And Zoom actually allow it to broadcast to different students. So student A, student B, student C. Okay. Everybody get the image from server, but my audio and video being captured to the Zoom. Zoom is a server. So you capture whatever I send, upload to later, and then Zoom will distribute to different person. Okay, so that we call it server. So this is a server you need to have to provide service. So the server can be YouTube server, okay, pre-recorded video, can be Zoom for live streaming, can be a game server, okay, game also have a server. So this is the so-called streaming, okay. And these are the streaming devices to help to make it work, okay. So video, we have different scenes, okay, these are okay. So here, this one is a video recording, okay, video recording. This one is video editing. And this one is video hosting. Video hosting means that you can host it by YouTube, that's pre-recorded video, or live like Zoom. Zoom is also a video hosting, okay. And you have the digital stage, okay, this is called video engineer. So video engineer handle the whole recording for the whole stage, okay. So this one's called video player. Video player has all kind of function on it, okay, all kind of function on it. This one called video playback. So video playback is that you got a video, you need to control how to play, okay. So that one, okay. Graphic, okay. So we talk about text, we talk about image, we talk about audio, we talk about vector, video. Now next one is graphic, okay. So graphic has a vector graphic and also raster-based graphic, okay. So raster-based graphic is like your JPEG is raster-based graphic, okay. That's raster-based graphic, okay. So raster-based graphic is like we have pixel by pixel, pixel by pixel. That's called raster-based graphic, okay. Vector graphic is different. Vector graphic is usually when we do font. Say we write a font, we don't want to have the artifact, okay. So we write a font. So when we write a font, it actually is using vector graphic, okay. So let's look at the comparison between raster-based graphic, vector-based versus, okay, vector-based, okay. Okay, these two things are different, okay. So let me put it into the tab, okay. So here, usually the vector base is using equation, okay, using equation. So it's using equation, so it's actually smooth because it's using equation. And raster base using the pixel by pixel. So you'll see something like this, okay, you'll see something like that. But equation, for example, you are taking picture, you cannot use a vector base because picture, you cannot actually take a picture by using equation. So usually JPEG or taking picture, you are using the raster base, okay? But you draw the font or drawing graphics, you will use the vector base, okay? So these are the two different type of the way to store image, okay, a graphic, okay. So you need to learn scalable, okay, scalable, resolvability dependent, and also EPS. These are some terms you need to know, okay. So SVG file is a scalable vector graphic, okay. Scalable vector graphic. See. Okay, that's actually a vector graphic, okay. So this is a basic idea you need to learn, okay. So this one, okay, because we are review, so I go a little bit faster to finish one up, okay. So we have that. Now let's actually try this, okay. Let's try to bring the second part for this data, okay. Let's bring up the second part for the data and the information. That's called data compression. Okay, this one is called data compression. The first part we have the data representation. So we talk about a bit, byte, okay, and then the storage of the data and file and different multimedia formats. Okay, so this one we talk about the data compression. We look at the different file type, and then now we talk about how to compress the data. Okay, so data compression. Data compression, we have two purposes to do data compression. This one is very important, okay? These two purposes, one is for transmission. The other one is for storage, okay? So why we need to do this, okay? Because when we do transmission, say I try to send email, okay? I will try to send email from my side to the other side, okay? So using email. So email usually is text. The file is not big, so that actually is okay. But if I try to download a video, okay. So for example, like a movie, okay. So the movie actually has, say, 30 frames per second. Okay, so 30 frames per second. Each frame actually has, say, 2 megapixels. Okay, each pixel has 4 bytes. Okay, 4 bytes, 1 integer. So only this one actually what? Actually right here, it's only 1 second. Okay, this is only 1 second. That's assume that actually I have 1 hour. 1 hour would be 360 360 seconds. So this one I will end up with what? 60 times 4. Okay, 60 times 4 is 240 times 3,600. This many mega. This many mega would be actually equal to 24 times 36 giga. So that's a lot of data you need to just transmit the file for a 1 hour movie. So if you do not compress the data, you basically cannot download it to your local because the data size is too big, okay? So we need to do compression on the data. So data compression is very important. Usually the video, you need to achieve the compression ratio about 100 in order to make it work, okay? Images such as JPEG will be around 2 to 13 data compression ratio, okay? So compression, we have two types of compression. One is called lossy compression. One is called lossless compression, okay? So lossy compression is that after you compress, the data cannot recover. That's called lossy compression. Lossy compression is that after your compression, data can be recovered. We call it lossless compression, okay? We call it lossless compression. Okay, so here, this one is compression. So we talk about two different types of compression. One is lossy, one is lossless, okay? And the purpose of the compression is because the file could be too big. especially you transmit the video over the internet. You take a long time, or you store the video to the hard disk. You take a big space. So usually, for example, my courses, I back up to my hard disk. Okay, I back up to my hard disk. So my whole hard disk back up my courses over the many years. Everything I actually compress them in zip file. Okay, so I do not put the whole directory to my directory. I actually store all the past courses video into the zip file. Okay, so that compression is very important, especially when you try to store it. Okay, or you try to transmit it. Two occasions you may need that. Okay, you may need that. So two ways you can do compression. One's lossy and one's lossless. Okay, one's lossy, one is lossless. Okay, so lossy versus lossless compression. Lossless compression algorithm allow you to reduce the file size without sacrificing any of the original data in the process. That's called lossless. Okay, and lossy means that you may lose some data. Okay, you generally able to restore your original file if you want. Okay, so roundness encoding and the LGW algorithm are both example of the lossless compression because they only shorten data to compress. Okay, so here these are the lossless versus lossy compression. Okay, so one can be recovered. That's actually lossless. Okay. So here you see that actually one is after compression, the other one is actually before compression. Okay, so actually I think that the right hand side is compressed. Okay, so right hand side actually the file size is 62% less. Okay, 62% less. But if you look at the image, you can almost not able to tell its difference. Okay. So for some applications, especially image or the video, usually we use the compression, lossy compression. You lose some data, but actually you achieve higher compression ratio. Okay. And if you use the text format, usually you don't use the lossy compression. Okay. So text compression. This word is very important, heuristic. Okay, so heuristic is a problem-solving approach. Okay, to find a satisfactory solution, and when optimal or exact solution is not practical. So if the optimal or exact solution may take a long time to finish, say 20 years to finish, then the computation makes no sense. We may use some program to finish 1 hour using heuristic, but heuristic usually would achieve maybe 85% of the original quality or 90% of the original quality. Then those kind of heuristic can be useful. Okay, so heuristic is one kind of algorithm. Usually people come up when the optimal solution or exact solution is impractical, then we will use a heuristic. Okay. So here we also have the lossy compression and lossless compression. Okay, so compression is decrease the number of bits used to represent the piece of information. So usually we have a file, say we have original file. Okay, that's consider that this one is actually F. Okay, and then we have a compressed file. Let's consider this is C. Okay, so the ratio of compression is, say you have your original file minus your compression size divided by your total size. Okay, this one we usually come up with the compression percentage. Okay, compression percentage. But sometimes we hear the word compression ratio. Okay. Compression ratio. Compression ratio usually is the original size over the compressed data file. So say original file is 10 mega, but after compression, you only have 1 mega. So you say the compression ratio is 10 times compression. Is that okay so far? Okay, this equation is very important, okay? Hi, Michelle, Wayne, are you okay?
Yeah.
So here we talk about two compression number. One is called compression ratio. When you want to find how many times you compress, you use the original file size divided by your compressed data size. That would be maybe 10:1 ratio. Okay, that's 10. Compression ratio is 10. But if you want to calculate the percentage, how much you compress by the percentage, is your for original file minus your compression file size divided by the original file size. That's your compression ratio by percentage. Okay, so these two terms sometimes you will see that. Okay, so lossless compression. There's one lossless compression called LZW compression. Okay, LZW compression is used for the so-called zip file. So you sometimes use a zip file. It actually is using compression. So now let's actually look at one video for the data compression. Okay. This one is from code.org. Okay, this one is from code.org.
Good grammar and spelling are important, but if you want to write essays that inspire,
my name is Aloe Black. I'm a singer, songwriter, and entertainer. When it became more and more important for artists to have a presence on the internet, I quickly developed the skill to build a website and get online, use my knowledge of coding to make it so that people could learn more about our music. Every bit of data or information can be stored digitally. Whether it's numbers, text, pictures, music, or video, all of it can be represented digitally. That means the information can be represented by electrical signals that are on or off, or as ones and zeros, so to speak. But representing information in ones and zeros can take up a lot of space. For example, if you wanted to store a 3-minute song digitally, it would take up over 30 megabytes of space. A 1-hour HD video would take 800 gigabytes. In the real world, digital information is compressed to take up less space. A 30 megabyte song can be compressed down to 3 megabytes. An hour-long video can be compressed from 800 gigabytes down to just 1 gigabyte. Sometimes compression is lossy, which means that to save some space, some of the information is thrown away. For example, an image can be compressed to a lower resolution to lose some detail. Lossy compression is useful because in many cases, the human eye or ear can't even notice the details that are being lost. When you compress data without losing any details, that's called lossless compression. This means the compressed data can be decompressed back into the exact original. One way of doing lossless compression is to find patterns in the data you're trying to compress. As an extreme example, imagine a book about dogs with hundreds of pages using only one word. Each page just says dog, 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 over and over 1,000,000 times. Instead of writing it all out, you could just store the pattern, dog times 1,000,000. Now that's a silly example, but let's look at a more real example. Instead of a book, imagine the lyrics of a song. If a single word or phrase is repeated a lot, you can store that once and then reuse it without repeating the data.
Let's see how this works with a simple text compression widget. This widget lets you experiment with compressing text. You want to represent the original text with as few bytes as possible. The widget lets you try compressing different ways and see it as it happens. Let's see how it works. The widget shows you some text to compress. In this example, lyrics to one of Aloe Black's songs. In the dictionary area, you can type patterns you see in the text. For now, let's just look for words that repeat. As you type in the dictionary area, a single symbol will be substituted in the main text area. In the example here, you can see each occurrence of the words I was has been replaced with a symbol of a sun, and I'm has been replaced with an umbrella. If you sent the compressed version of the lyrics to someone, you'd also have to send along the dictionary.
Okay, so here one thing is very important. Left-hand side is your data, okay, your data you want to transmit. Right-hand side is called dictionary. So this dictionary, sometimes we also call it code book, okay? We also call it code book. This one, sometimes we also call it code book. So a sun represent I was, a umbrella represent I am. So basically you need to send the compressed data, also the dictionary to the destination. So your efficiency, your compression, this compression ratio, you should include the compressed data and also the dictionary. That's your C, okay? Your original file size minus that one divided by this. The C should include in the compressed data file and also the code book, okay? And also the code book. Both of them, you use that to look at this compression ratio in percentage, okay? Is that okay so far? Hello, is that okay so far? Angela, are you okay?
Yeah.
So remember this, how to calculate this compression ratio.
So that they could reconstruct the original text. So the question is the total number of bytes in the compressed text plus the bytes in the dictionary less than the number of bytes in the original text? The answer is yes for our current example, and the widget shows you how it's calculated. We assume that every character that needs to be sent takes 1 byte. So the display shows the compressed version of the lyrics with the symbols substituted in it has 216 bytes or characters. It also shows the number of bytes in the dictionary as 10. This is to store the words I was and I'm, also the symbols that represent those patterns. This gives us a total of 226 bytes. We can see that the original text had 240 characters or bytes, so we reduced the bytes needed to represent the poem by 14 bytes, or 5.8%. Not a bad start. Looking for words that repeat is a good start, but you can look for other patterns. Sometimes a repeating pattern could be a subpart of a word or many words. Here's where it really gets cool. You can find patterns that include dictionary symbols you just made. For example, we replaced words I was with a sun symbol, but now you can also see that a new pattern, didn't know, sun symbol, lost. You can type this in the dictionary too. As a side note, to enter the sun symbol, you need to copy and paste it, unless your keyboard has a sun on it. With that little change, we're now up to 26% compression. Try it yourself and see if you can do better.
The repetition in a song lyric or poem is obvious, but really any form of information can have repetition or patterns in it. They're just not as obvious. For example, an outdoors photo can have a blue sky, and instead of storing every single blue pixel, that can be compressed. With the amount of information that's digitized and sent around the internet every day, there are much fancier ways to compress the data. Data compression is now built into how every picture, or song, or movie is stored, and almost every web page you visit is compressed as it's sent to your device. All these compression algorithms have one thing in common. They all aim to represent the information in the smallest format possible, in a way that can be decompressed to reconstruct the original, or at least something close to it.
Okay, so this one is about data compression, okay? Overall idea of the data compression and how the compression ratio being calculated, okay? So we skip this portion for human compression, okay? Let's look at another thing. So this compression ratio we already know. So next one is heuristic versus the exact solution. So heuristic is maybe 80% correct, okay? Maybe 80% correct. And exact solution is actually 100%, but exact solution sometimes is very difficult to find. Okay, so we find some heuristic. Okay. So the efficiency of the compression algorithm is actually content dependent. So sometimes some content in the video is said that actually the repeated pattern. Okay, so you need to find some pattern. If your data don't have the repeated pattern, it's very hard to compress it. Okay, so pattern recognition is a keyword. It's a keyword. How you recognize the pattern and do the compression. Okay, so now let's look at another video that actually doing the compression in real world zip file. This zip file is using the so-called LGW compression, and this one is the best lossless compression. Okay, lossless compression. You won't lose the data, and you will achieve higher compression ratio. Okay, this one is the LGW algorithm. Okay, let's look at this compression video.
Every day we are creating and communicating billions of terabytes of digital data. If it were written on paper, it would represent millions of libraries worth of data created every day. So we are always looking for ways to squeeze more data into less space. One approach is to design smaller and smaller memory media. But no matter the medium, there is a second mathematical tool we can use if we take advantage of the patterns in our data. We can use them to compress the size of our files as much as possible. The challenge is to do this compression in a way that enables us to reverse the process and uncompress the data without losing any information. This idea is known as lossless compression. Before the era of computing, we confronted this problem whenever we communicated over long distances, when we wanted to shorten our messages without losing any information. For this, people devised codebooks which map a specific set of common phrases into short letter sequences or codes using a lookup table. For example, the Siemens codebook contains common phrases used at sea, such as "I have one anchor on board," which can be expressed in code as AAC. While the Cotton Merchant codebook maps the phrase "our prices are below surrounding markets" to the word glass. So if two people share a copy of a codebook, they can communicate long phrases in just a word or two without losing any information. But there is a problem with this codebook approach, because these codebooks don't contain every possible sentence you might want to send, just the most common sentences for a specific kind of conversation. And if
so in the old day, the codebook actually is like a dictionary, but because the dictionary cannot be exact, so you can only use the codebook with limited content. And that actually is a problem.
The type of conversation changed, the codebook would no longer be usable. This problem leads us to a more general approach where a single codebook is used no matter the type of conversation we are having. For example, one way we could do this would be to create a codebook based on the words of a given language. The idea is to map common words in any language to shorter sequences and to map the less common words to longer sequences. This approach is nice because all possible conversations in a language can be compressed using a single codebook. While this codebook works in general, no matter the conversation type, the compression achieved with this strategy is not as good as the codebooks designed for a specific kind of conversation. So we are left with a key problem. How can we achieve the high compression of conversation-specific codebooks while maintaining the simplicity of using a single general codebook which works on all possible conversations? A solution to this problem was presented in a paper published in 1978 by Jacob Ziv and Abraham Lentil, leading to what's known as Lentil Zip Compression. The main idea behind this paper is that we should build a new codebook specific to every message we send. That is, we could take each message we want to send and scan it looking for repetition and design an ideal codebook for that message, which maps the most common sequences in the message to short letter sequences. The sender can then use that codebook to compress the message. But of course, the receiver won't know how to interpret the data unless you first send the codebook as well. The goal would therefore be to design this codebook such that the codebook plus the compressed message is shorter than the original message.
Okay, this one is very important. Your compressed message plus the codebook need to be less than the message. Okay, so the codebook's transmission is a problem. If you send a super big dictionary, your compression means useless. Okay, so there is a problem of how to make the codebook as small as possible. So this the Lentil Zip Compression come to the conclusion that they can achieve a way to do compression without even sending the codebook. So that's their major contribution. Okay.
This is critical to make this method work. And then the sender can send the compressed message with the codebook attached. The receiver then uses that codebook to uncompress the message to get back the original. Because a dedicated codebook will compress a message so effectively, the compressed message plus the codebook will compress better than if we used a generalized codebook. What the extra insight Ziv and Lentil had was to construct the codebook on the fly, eliminating the need to send the codebook and decreasing the delay in codebook construction. The trick was to rethink how the codebook is constructed.
Champion artificial intelligence and build the most cutting-edge apps of the future. How?
Instead of scanning the whole message to determine an ideal codebook, which is then used to determine the compressed message as before, the codebook and the compressed message are built on the fly. So at first, the codebook is empty, and as the message is scanned, the sender gradually builds up a codebook based on the letter sequences as they occur. The compressed message is also created at the same time using whatever is in the codebook at each step. So gradually building and applying a codebook on the fly allows the sender to send only the compressed message, because the receiver now has the ability to create the same codebook as the sender using the compressed message by simply performing the reverse operation as the sender. And that's the key insight. To see how this works, let's do a simple example. Let's say that Alice wants to send Bob the following message. Now remember, both sender and receiver start with empty codebooks. And the sender's encoder scans the message letter by letter, stopping anytime it encounters a letter or letter sequence it hasn't seen before. At first, it will always stop at the very first letter, in this case, A. And then it compresses that sequence using whatever is in the codebook at that moment, which is initially empty. So it sends the letter with the empty symbol attached to signal that it's the first time it's seen this letter. And since it's the first time the encoder has seen the letter A, it's added to the codebook as the first entry. The receiver does the same thing. The A arrives, and it knows it's the first instance of the letter A, so it adds it to its codebook in the same way. And the sender outputs A as the first letter in the uncoded message. Then the sender proceeds to the next letter, A, which it has seen before, so it grows the sequence by scanning ahead one letter to B to form the sequence AB. Since it's the first time the encoder has seen the letter sequence AB, it stops here. Instead of sending the sequence AB, it compresses it according to what they know is in the receiver's codebook up until that point. And this will always be the current sequence minus the last letter. In this case, this is A, which is in our codebook as A equals 1, thus sending AB as 1B. Finally, it adds this new sequence AB to the codebook as entry 2. On the receiving end, 1B arrives, and the decoder knows that 1 equals A, and so it outputs the uncoded sequence as AB, and then it adds AB equals 2 to its codebook in the same way as the sender. The sender proceeds to the next letter, A, which it has seen before, so it scans ahead one letter to B, leading to the sequence AB, which it has seen before, so it scans ahead again to form the sequence ABB. Since it's the first time the encoder has seen the letter sequence ABB, it stops here. It compresses it according to what they know is in the receiver's codebook up until that point, for that sequence minus the last letter, in this case, AB equals 2. So it sends ABB as 2B, and it adds this new sequence ABB to the codebook as the third entry. On the receiving end, 2B arrives, and the decoder knows that 2 equals AB, and so it outputs the uncoded sequence as ABB. It then adds ABB equals 3 to its codebook in the same way as the sender. The sender proceeds to the next letter A, which it has seen before, so it scans ahead one letter to B, leading to AB, which it has seen before, so it scans ahead to form ABB, which again it has seen, and so it moves ahead to ABBA. Since it's the first time the encoder has seen the letter sequence ABBA, it stops here. It compresses it according to what they know is in the receiver's codebook up until that point. In this case, ABB equals 3. So it sends ABBA as simply 3A. Notice this time we compressed a 4-letter sequence down to 2. Finally, it adds this new sequence ABBA to the codebook as entry 4. On the receiving end, 3A arrives, and the decoder knows that 3 equals ABB, and it outputs the uncoded message as ABBA. It then adds ABBA equals 4 to its codebook in the same way as the sender. The sender proceeds to the next letter A, which it has seen, so it scans ahead to B, leading to AB, which it has seen, so it scans ahead one more. Since it's the first time the encoder has seen the sequence ABA, it stops here. Instead of sending ABA, it compresses it according to what they know is in the receiver's codebook up until that point. In this case, AB equals 2. So it sends ABA as 2A. And finally, it adds this new sequence ABA to the codebook as the 5th entry. On the receiving end, 2A arrives, and the decoder knows that 2 equals AB, and so it outputs the uncoded sequence as ABA. And that's how it works. Notice the sender is always adding what it hasn't seen to a growing codebook, and then sending that sequence minus the last letter in coded form using what they know is in the receiver's codebook. That's the trick. In this example, we're using a communication context, but even outside of communication, anytime we are storing data on hard drives, this method is used widely, from compressing DNA sequence to the popular zip compression protocol. It's also a key component of the GIF image format used when you compress images for rapid loading on the web. Aside from communication and storage, realize that this process is also learning about the data itself. It's scanning the data and building a model of the underlying statistical structure in real time. This led to applications in both pattern matching and machine learning. Without this algorithm and the ideas it inspired, you likely wouldn't be able to store as much data as you do or stream this video in the first place.
Okay, so this one tells you what is zip, okay? You may use zip before, but this one tells you what is zip, okay? And zip can do compression without sending the codebook. That's the main whole purpose, okay? And this one is very important because it's the widely used data compression scheme. So this we today so far let's actually for the lecture let's start over here. Okay, we finish up to this lossless compression. Lossy compression we'll talk about it next time. Okay, so now let's do one thing. Okay, let's do one thing. Let's go back to our website. Okay, number one, this course. The students should have this, should have your account to access it, okay? Everybody has it. If you haven't logged in, you should, and you are required to submit the homework, okay, already for week 1. So today, you need to work on the week 2 already, okay? So that's the first thing. Second, some students ask like where to find the slices, okay? Where to find slices, you need to log in this account that we gave you, and then find this course CS51. Okay, this is where you need to submit the homework. Okay, So here, today we are on the Unit 2, okay? Unit 2, here the slices are over here, the lecture 2A data representation. Okay, so this one is the PDF file you can get, okay? This one is the PDF file you can get. And also the second part is the data compression portion, okay? So data compression portion is lower here. You should see 2B, that's lecture 2B, the data compression portion, okay? So now there are several quiz you will do auto grading, okay? And extra reading material and the video, but we don't have time to go over them, all of them, because they are regular year material. So now let's look at this one, Unit 2, data unit test, okay, together. This one, let's work together, okay, or to review it, okay. So I will have students to help me to answer, okay. So Unit 2 data, okay, this one, let's actually look at Unit 2 data. Okay, here we have about 20-something problem. Okay, 20-something problem. Let's work on it one by one. Okay, so you will know what kind of problem will be tested. Okay, you know what kind of problem will be tested. Okay, so now let me actually find someone to work on it. Okay, let me go from the bottom. Okay, the first one, Tao Liu. Okay, Tao Liu, you can you work on the first one?
Okay.
Which one give you the most compression?
It was either A or B, right?
Yeah, A or B. Lossy or lossless. Which one give you more compression?
They're both like loss. I just remember the loss part. I forgot the other. Is it lossy?
One's lossy, one's lossless. Lossless, you can recover the data. Lossy, you cannot.
Oh, okay. So it's lossless.
No, the answer is A, lossy. Lossy one, you do JPEG, you cannot recover the data, but
yeah,
the compression ratio will be higher. Okay. So
Okay.
I told you this actually the kind of material we teach is very important. Okay.
Mhm.
Okay, the second one, we have Sunny. Okay, Sunny Yan. Problem 2. Which of the following best describe abstraction?
D.
No, the answer is B. Abstraction is using the simple thing to reduce the complexity. Remember that? Abstraction is to reduce the complexity. We talk about it when we using the maximum function, and the maximum function has the x and y, and the whole function inside we don't need to care about it. We just call the function. Okay. Or originally we have 5 stone. We represented some data. Let's call abstraction. Is that okay? So here, I mean, we go over the lecture and everything we talk about is very important. Okay. It's very important. It's okay. We just try to review. Okay. Sunny, is that okay? Hello, Sunny, is that okay?
Yeah.
So number 3, we have Ryan Wu. Okay. Why is cleaning data important?
Would it be D?
Yes, it's D or above, because you get a raw data. Raw data, for example, some student has a SAT exam, but the scan is not clean, okay? You have to recover the data. Some people fill in the wrong name even, right? So the cleansing of the data is very important. So it actually is all above, okay? Number 4, let me have Nico Wei, okay? Number 4.
A.
Hmm? Which one?
A.
A. This one actually, in analyzing the data, indicate the company should hire people with college degree because they stay at the company for longer. Okay, so this one talking about your data. So your data, you may have high school graduate, you may have associate degree, you have a bachelor degree, you may have master degree, you may have PhD degree. Okay, so this one is saying that okay, the bachelor degree will stay in the company for longer year. Okay, so that's assume that the analyzing the data, okay, the data and then indicate that you should only hire the people with the bachelor degree because it stay for longer. Okay, what is the potential indication of this? So this one actually is what? This one actually, if I choose B. Okay, frequency analysis to identify commodity in data. So we actually try to find which one open the most. Okay, the textbook say C. Okay, C. Okay, the book give the answer of C, but I actually do not see the bias here. Okay, so this one actually is very controversial. Okay, I do not agree with the book's answer. Okay, is that okay?
Okay.
I think that what he say bias is that okay, maybe because of the diversity of subject, he say that okay, you need to hold a bachelor degree. That's actually a stereotype problem. But here it already say that you analyze the data. Based on the data, why there's a bias? I don't see the bias. I do not see a bias. If the data show that bachelor really stayed in the company for longer, so why not? Why not hire more bachelor degree holder, right? So here I don't see the bias part, okay? So I do not agree that one with the book. Number five, let me see, we have Nathan Chen for number 5. In which way the number system are upchecked?
Is it A?
Yes, it's A. It's abstraction because you have 5 stone. We do abstraction to 5. We do abstraction to tally chart. We do abstraction to Chinese 5, right? I talk about it. So that actually you can have different number systems to represent it, even 101 for binary number. So that actually is the abstraction, okay? So number 6, let me go to Michelle Wynn.
A.
Identify a pattern the human cannot see. Number 6, yes. We do data compression. We do a lot of things. We analyze data. Usually, we try to find a pattern. Okay, so it's a pattern recognition. Pattern recognition is most important part in machine learning and AI. Okay, so that's why analyzing the data to find a pattern is very important. Okay, number 7. Let me have Kathleen Lee.
Is this C?
Yes, binary data. This one's easy. Number 8, let me have Zhang Liu. In the lecture, I explained what's the overflow, what is the quantization error.
I know. I'm trying to think.
Which one it is?
C.
C, yeah. You do not have enough bit, that would be overflow. Okay. Overflow means that your data exceed the number of bit It's the possible representation that you can have. Okay. Quantization error means that you have more fractional bits, but you just throw them away. Okay. Number 9, let me have Angela Su. Okay.
It'd be A.
Which information is the author of the document is actually metadata. Yes, number 9 is A. Number 10, let me have Alex Zhang. Okay. When you do data compression, what is the main part you try to do compression? Why you can do compression?
C.
No, the answer is B. C is the reason why you need to do compression. But you can do compression because you need to find a repeated pattern. Remember that? Repeated pattern. Repeated pattern means that the video said that there's a picture and there's a blue sky and then the whatever blue times something. Remember that? Because you have A, B, B, A, you change this one to 3A. Remember that? That's a repeated pattern. And you put a repeat pattern into the combo. Remember that? Hello? Is that okay?
Yeah.
So we show this, you can see that whatever we teach in the lecture is very useful, okay? Must pay attention to it, okay? Number 11, go back to Tao Lu, okay? Tao Lu, you, number 11.
Okay, let me see. C.
C, yes. It's a process of processing the data is actually what is a data science. So data science is no different from other science. It's by developing the hypothesis and question the test. Is okay? Data science is nothing different from any other science. So it's also building the hypothesis and test on it. Okay. Number 12, go to Sandy, is actually converting this one to binary. You see, you are required to do that, okay?
B.
The answer is C. Okay, let's look at it. Okay, this one, I told you don't use a binary. You take longer time. So you use this one divided by 16. So 116, you have 54, right? So you will have 3, like 48, then you have 6. So 13 remainder 6. So 13 is actually what? 1101. 6 is 0110. Wait, let me see. B is the answer. So this one number 12. B is the answer. You say B, right? Okay, anyway, B is the answer. So is that okay?
Yeah.
So 13. So you must remember that you must be able to convert hexadecimal to bits pretty quick, okay? Also decimal to hexadecimal pretty quick, okay? If you use the divided by this one, 212 divided by 2, that's okay. That'll take a long time. That will take a long time, okay? Number 13, let me have Ryan Wu, okay? All right, are you okay?
Would you say my name? Sorry, my audio is
Yeah, I
kind of bad.
just say your name already. 13.
13? Okay. Would it be D?
Yeah, the answer is D. This one actually, the reason why we do an extra study, okay, can be many, okay, can be many. Let's think about SAT, okay. So when people ask that, is SAT, can SAT predict the success of the college life or not, okay? Can we use the SAT to decide that? So there's an argument. There's argument, so you need to find out, okay, how to understand the relationship between the variable. So SAT versus the income that after the student graduate, that's one thing you can study, okay? So single source cannot provide enough information, so data cannot provide it. So how about number of PhD created? That's another. So this one is also correct, okay? This may not be actual cause and effect. So some people say that SAT is a cause effect. So we continue to investigate about possible other things, okay, to study whether SAT is a viable tool to estimate the success of college or not, okay. So the answer is all above, okay. Next one, let me have Nicole Wait, okay, Nicole, number 14. Is converting the binary back to decimal.
Is it C?
Is C, yes. This one, actually, you have this one, right? So here you may have something like 13. So 13 plus this one is actually 64. So you get actually 77, okay? Another way to look at it is that, okay, this number will not be 1000, so this one you cross out, okay? Second, you see a 1 over here, so it must be an odd number, so it can only be C. Is that okay?
Yeah.
Is that okay? That's another way to quickly find the answer, okay? Number 15, let me have Nessa Chen.
14.
15.
Oh, 15. Is it B?
Yes, metadata is data about data, okay? Remember the term, data about data. Number 16, this one we have Michelle Wynn. Michelle.
C.
No, should be B. Integer can be stored precisely in computer. It's just 32-bit, precisely. Fractional number, real number, it cannot be stored in precise. There will be quantization error. Is that okay? Is that okay?
Yeah.
B. Boy. 16 boy. Is that okay?
Yeah.
Integer you can store precisely. Yes. Integer, yes. 1 is 1, 2 is 2. 1.255 that may not. Okay. Number 17. Okay. Number 17. Let me have Kathleen. We talk about sampling today. Okay.
Is this C?
Converting analog to digital. Yes. D. Doctor. Is that okay? D.
Yeah.
So the number 17 is D. That's AD, analog to digital conversion. Okay, sampling. Number 18, okay, an example of metadata about sea turtle nest should be, so this one, we have Jiang Liu. Okay, Jiang.
Which one?
Number 18.
Okay.
First, you need to know what is metadata. Metadata is data about data.
It's the B, the location.
No, the answer is this number 18. The answer is D. Okay, so let's think about this. You are trying to actually look at this one. You have the sea, you have turtle, right? Ocean, you have sea, okay. You have turtle over here, okay, whatever, turtle. When you look at the sea turtle, whatever, that's content already. So metadata is somewhere up in the air, the tracking number, the ID for this case. That's data about data. Is that okay?
Mm-hmm.
If you are trying to look at the data itself, that's data itself. Does that make sense? So also doesn't have to do with the image. It is a girl, it is a car, we don't care. The author is author. Is that okay? That's called metadata. It's data about data, but not the data itself. Number 19, okay, number 19, Angela Su, okay, number 19.
19 would be A.
Being able to add or remove resource to store large data set is called A scalability. Okay, you can scale up the design. Okay, so that's called scalability. Number 20, okay, about data compression, Alex, okay.
C.
Number 20, Alex Zhang, okay.
Oh, yeah, C.
Data compression algorithms are used when data were too large to send in timely format. So the answer is C, yes. The answer is carrot, okay, C. Number 21, okay, number 21, this one for, go back to Tao Lu Yu, okay, Tao Lu.
Okay. Is it D?
The answer is C. The answer is
okay.
C, okay. But this one, I would say this one is poorly designed problem, okay. The author doesn't design it well, okay. 32-bit computer, it actually mean the computer. So if they say that 32-bit address, okay, 32-bit address, and then 32-bit memory space versus 64-bit memory space. So it's a 2 to the power 32 versus 2 to the power 64. So it would be 2 to the power 64 divided by 2 to the power 32. That's actually 2 to the power 32 times more data. But the problem description is not clear, even though I will pick C if no other clue, okay? But this one, the description for it is actually not clear. Is that okay? It would be 2 to the power 34, divided by 2 to the power 32. That is the number of time of the address space that the 64-bit computer can be stored compared to 32-bit computer, okay? But it will not be 2 to the power 36 minus 2 to the power 32, okay? So, and also it's not number of bit more, okay? So this problem is not well designed, okay? The author actually not carefully designed this problem. So, but anyway, C is some closer answer to pick. The next one, Sandy, number 22.
D?
The book say the answer is B, okay? The book say the answer is B, okay? I say this one, no answer. It should be logical error. Let me explain it, okay? So you said that you had actually say COVID-19, you try to test the patient's temperature to determine whether he has a fever or not, okay? He has a fever or not. So you test it. If your number is actually 98.6 degrees, then you have a fever, right? You have a fever. So what he says actually your temperature equals 98.6, but because it's a 14-point number, so you may have round-off error. Is that okay? Is that okay? Hello, Cindy, is that okay?
Yeah.
So that's you compare to 14-point number, that's not exact. So the book say B, but I don't agree with this. It's because that this error is not like that. Okay, the error is really unity greater equals. That's logical error, right? Because anybody above 98.6 is considered to be have fever, not exactly the same as 98.6, right? Am I correct? You say you have a fever. Should you have a fever only when you are 98.6 degree F, or you have 100? You also have a fever. Which one? So it should be greater or equal, right? So this one also had a logical error. Am I correct?
Yeah.
You cannot use an equal to check whether you have a fever or not, right? Who use an equal to check a person has a fever? So this one also a poorly designed problem. He's intended to answer is B, but I don't agree with it. I would say the condition. I would say D. The test condition is invalid. Okay. It's a logical error. It's okay? You said D, right? You're actually correct. So it actually is a logical error. This one is a logical error. We pick D, okay. So number 23, okay, number 23, this one, Nico, please. Nico, wait. So you're given such a table. What can you make a conclusion here from this table?
C.
No, this one actually, the answer is D. Okay, this table, can you see which is popular, McDonald's or actually KFC? You don't see that, right? So you cannot make a conclusion on who is the most popular item. Okay. And day of field trip that the missed class. Do you have that? The field trip, whatever. You don't have that. And then days with highly absentees. Do you see the absentee? No, you don't see that. Maybe they are more guests. So this why you don't see that. So you have that overflow. You can only make conclusion that amount of wasted budget dollar. Is that okay? Based on this table, you can only make such a conclusion. Okay. So number 23 is like that. Number 24, Nathan Chen. Okay.
Is it B?
Okay, a company purchased a large block of data from social media sites. So basically, for example, Amazon from purchased larger block of data from. I'm sorry, actually, Facebook buy data from Amazon. Okay, whatever, either way. If they want to analyze the data to learn more about potential customer, which technique should they use? Okay, so you need to identify a pattern. Yes, identify it, and for further study. Is okay. So who buy more pencil? and use that to find a potential customer, right? Is that okay? Or who browse the pencil page more? Okay, so that's the B. Okay, that's the B. Targeted marketing. Okay, you try to find the target market, try to study the pattern of the behavior people use a website. Okay, so number 25, Michelle Wing. Okay, 25.
B.
B. Okay. Let's actually look at 1 and 3. Which one is bigger?
1.
1 and 3. 1 is bigger.
Oh no.
3 is bigger, right?
Oh yeah.
3 is bigger.
Oh.
So 3 bigger than 1. Okay. Then this decimal we need to convert it to what? To binary. So when we convert it to binary, we have 1, 1, 1. We convert it to binary. So this one that's divided by 16. Okay. So we have, say, 6. We have 96. Okay. So this one will be 515. So actually is what? 6 is 0, 1, 1, 0. Okay. 1, 1, 1, 1. Okay. So this one actually is 1 greater than 2. So the answer is C. Okay. The answer is C, but the book say B. Book say B is wrong. Okay. So this one again, the book had technical error. Is okay? Is okay?
Yeah.
The answer should be C, not B. Okay.
B.
B. Okay. So this one actually is what? You know that this magnet school, say hacker. Okay, say hacker. Hacker actually has trying to recruit the people to go to their high school, right? So they are boosting their AP successful rate. Okay. So how can you try to do marketing in a better way? You post an image of the student result to the social media. That's actually okay. Creating a pie chart, okay, and post it to the school website. That's also okay. And then it should write a report about marketing profit. This one is text, okay. So here you have a text, you have an email, you have an image, and you have an animation. So B win because it's actually animation, okay? Is that okay?
Yeah.
But this one actually makes no sense. It actually in real AP exam, I think this one will be criticized, okay? We picked that because if I do marketing, I may do that, but this one is arguable. It's a personal preference actually. So A, B, C, D actually everything work, okay? And the high school will do all of that. All are way to actually recruit students. But you say that, okay, actually, which is the best method? Who knows? Maybe sending the website using image is better. Okay, so we don't know. We actually don't know. Okay, that actually, but it's not something we can verify as a student to take exam. Okay, so not number 27. This one actually Jiang Liu. Okay, Jiang.
Which one again?
27.
Okay.
We only have one problem in the video.
D.
Which topic? Why D?
Wait, what does it mean by which topic?
I don't know. Then why you pick D?
No, because if it says if I were to analyze data and get the most insights out of something, it would be from the standard test score compared to what the students got in the past.
Then that's the typical. These are 4 topics. You have A, B, C, D, 4 topics. Which one need to use to program to analyze the data to identify insight. So average, student drive to school, you just calculate the total number of the student drive to school. You go to the parking structure and look at how many cars there. That's the average number. You can do that. Okay. So do you need to do an analysis of the data? No, you don't. You just do recording. That's raw data sampling is okay. The record of win or loss, this one also just raw data. The say San Francisco 49er is a 10 win 2 loss. That do not need to do analysis, right? The number of library book, okay, need to review. Look, you go to the library, check if the book is ready to be used or not. Then that actually you can see how many books need to be repaired or replaced, right? So ABC, none of them need to do analysis. You just count the number. That's actually raw data enough. You do not need to do analysis. So the standard test, this one you need to do analysis because you need to look into the insight. Whether student mess up in the algebra 2 or algebra 1, that you need to do study or geometry. Okay? Or geometry. So don't look at the book, okay? Don't look at the book. Try to answer by studying the problem, okay? We are discussing. Number 28, okay? Number 28, this one for Angela Su, okay? This one is a long problem. Let me minimize it a little bit, okay? So you can see the whole picture.
Would it be E?
Okay, this one, let's look at this, okay. This one is said that, okay, which information can the school district obtain from the following data that have, okay? What the goal is to analyze who attend local community college, okay? So here I would say this is a chunk of data totally useless, okay? If you read this one, you are wasting your time. So let's look at it, okay? The school district want to analyze data about a high school graduate who attend a local college. So every number of each state student who enroll in local, we have school districts, so average each state, there's nothing to do with it, okay? If the number of local graduate who enroll in a local community is increasing or decreasing. So here, this one increasing or decreasing is not actually doing analysis about a high school graduate attending the local college. That's actually yes. Number of local high school students who graduate from, we don't see that, right? This one actually, number of high school students who graduate from local community college. Okay, we don't see, it's actually certain discrete school district must be related to the school district. That's one popular program in the community. This one is not, okay. So this one C is not because it is talking about graduation from the local community college. But graduation number doesn't mean that because you have a lot of local community college students actually will transfer to 4-year college. So if you use the graduation number, that cannot represent the number of students who enroll. We are looking at the attendance. Is that okay? Is that okay? The data for graduation already has some transfer and someone who actually graduate. So the transfer portion is not being calculated if they do transfer, but without getting a degree, or they drop in the middle. Okay, so these two numbers are different. Cannot imply that the graduation. You can use that as a reference, but cannot predict the exact number. Okay, it's okay. So that's the review for today. Okay, any questions so far? Okay, so we go over the different topic. Okay, we go over the different topic, and those topics we go over. As you can see, we check these different problem. You will see those problems in the real exam. Okay, and let me know if you have any question. But this week, please, we already need you to finish the. Let me see here, the week 1. Okay, week 1 right now. Okay, let's look at the total number of the return. Okay, week 1, this one actually only roughly about 6 people, 36 students, only 6 return. Okay, and the college board exam actually also only 6 students. Okay, so very low turn in. Okay, very low turn in right now. Okay, and next week we will have the due for week 2. Okay, so please practice more. Okay, next week Friday night we would have due for the week 2. These 2 data and information, and also pre-sentence review number 1. Okay, please turn in more. More practice will help you. Okay, right now the turn-in rate is really too low. Only 6 students turn in out of 36 students. Okay, thank you. Bye now. Bye bye.